Malbec Labs. Wanted to talk about DoubleZero and some of the content that we shared at Breakpoint in Abu Dhabi. For those that weren't able to attend or missed the session, we shared a couple things about the state of the network, about client route liveness, and our thoughts around observability, and then importantly, we talked quite a bit and showed some use cases and performance of Multicast. We'll talk a little bit about what's next, some of which has already started now that we're into 2026. We're sort of off and running. So I wanted to start with the state of the network. The state of the network is dense and active. We have instigated through the DoubleZero protocol quite a physical network. This backbone rivals those of any centralized organization. And importantly, our network is a community effort. There are 9 active network contributors that are offering high-speed interconnects between 28 different metro regions in the world. And there are 6 more on the way, actively building to contribute additional routes. And if you had asked me this time last year whether the network would be this dense at this stage, no, I don't think I would have said yes. This is an amazing effort by the community, and I think that anytime you go to build, something physical, a physical infrastructure, it always takes more time than you think. And I'm incredibly impressed with the talent that has gone and energy that has gone into building this infrastructure. When we think about the top line metrics that we're looking at to quantify the size of the network and eventually its impact, we think about the contributors. How decentralized are we? We have 9 active, as I mentioned, and 6 building. There's 28 metros, but there's 48 physical buildings, the data centers, right? So even though we're in already 28 cities, in many of those cities, we're in more than one building. And I think that's an important distinction to draw from just talking about the metropolitan area, because we also need to think about the diversity within the metropolitan area. Across those 28 metros, we have 75 active switching devices. There's 403 staked Solana nodes that are on the leader schedule, connected up to the network. And a really important metric that I introduced at Accelerate this summer is the MLU, the concept of an MLU. That's the maximum link utilization throughout the network. And this is important because MLU is really the early warning sign of performance problems that happen as a result of congestion in the network. We always want to be driving that number down. So you always want far more capacity than is needed, because in those moments when you want to burst, you want there to be plentiful bandwidth to sustain any sort of economic activity that might want to go across the network. So 56% we observe in Amsterdam, in that metro area. There's quite a lot of Solana stake in that area of the world, and that's where we see the maximum utilization of the network at this stage. Next, I want to talk a little bit about RFCs. Just as Solana has the Solana improvement documents, or SIMDs, the IETF originated this idea of a request for comments, or RFCs. This is a development pattern we really like, and we think in many ways, as we're developing protocols that are the DoubleZero, that allow for the DoubleZero network to be built, in many ways we want to give a nod to the IETF. And so we've done so through the development of RFCs as the basis for how we add features into the infrastructure. So you can visit malbeclabs.com/RFCs to get a sort of landing page that wraps around our GitHub page where you can read all of these RFCs in detail. And we're going to highlight one of those RFCs next, which is one that is in active development and about to be deployed into the DoubleZero testnet, and that's called Client Route Liveness. Client Route Liveness, it maybe speaks for itself, but in case it doesn't, let's talk about what it does. From the point of view of any DoubleZero connected computer running the DoubleZero client, the Client Route Liveness protocol emulates bidirectional forwarding detection. So BFD is an IETF standards-based protocol that's in use all over physical infrastructures to detect the liveness check of the other side of a circuit, for example. And in the context of DoubleZero, we think this is important because it gives us an angle to have, from any one client's point of view, a way to actively know whether a route received from the DoubleZero network is in fact reachable. So a bad situation would be that DoubleZero is sending your client routes and you try to use those routes and they go into the ether or a black hole. So if DoubleZero is in certain failure modes, it's possible while unlikely, and we want to protect against those situations as unlikely as they might be. So client route liveness is a way to do that, and we're going to be rolling that out into testnet here very soon. And so why should you care about this? Well, as I mentioned, it's faster detection when destinations become unreachable. So if your client is actively connecting to and observing packets from all the other clients on DoubleZero, well, when one becomes unreachable, the DoubleZero client can now withdraw the route, delete it from the kernel routing table. And in many cases, this can happen before the normal convergence would happen using the Border Gateway Protocol or BGP. The folks at Anza have developed last year with us a sidecar Python application that largely did this. But we feel very strongly that this become a first-class part of the DoubleZero client. And so that's why it's being built, and that's why the protocol is about to be rolled out. Importantly, the overarching goal here is to reduce the risk of sort of corner case failure modes impacting Solana more generally. Next, I want to talk about observability. We think about observability as a real differentiator for DoubleZero when compared to the public internet. Any designer of a high-performance system should want to understand how the physical infrastructure that underpins that system is performing. It's very difficult to obtain metrics and performance data for the public internet, and we aim to make that as easy as possible at DoubleZero. We look at it through three lenses: performance, availability, and the topology itself. Now, there's more than this from an observability standpoint, but these are the three that we're attacking first. From a performance perspective, we sort of have two angles. There's the raw performance of the individual circuits that make up the physical DoubleZero network. We write those performance statistics down on chain to a public ledger that can be verified, and we do that for the basis of the rewards. So the rewards for the network contributor community within DoubleZero is based on a Shapley value calculation, and the basis for that is the comparison of the latency that is actually observed in DoubleZero versus the latency of the public internet. Now, aside from rewards and driving sort of toward the best possible latency scenarios, we also want to observe the time series performance of the network, latency, jitter, throughput, utilization, errors. And so we write that information from every contributor's DoubleZero device to a publicly available influx database. And we put those dashboards available, or make those dashboards available at metrics.doublezero.xyz. Very soon, we'll be releasing a new dashboard on the metrics page, and this is around availability. Now, we had a situation occur late last year where a DoubleZero user reported that they could connect to one of the Solana validators that had been connected to DoubleZero. They could connect to its TPU via the public internet, but when they connect their computer to DoubleZero, they could no longer connect. This situation turned out to be a corner case where the validator that was unreachable was in the middle of a hardware upgrade, and their connectivity to DoubleZero was affected as a result. But it got us thinking, we really should take a global viewpoint on TPU reachability. So one of the dashboards that we've recently been building out is from a variety of source locations worldwide, can we reach the all of the TPUs that are connected to DoubleZero from both the public internet and via DoubleZero. And so very soon we'll release this dashboard and make this available, not just the availability, but also the performance characteristics from, again, variety of source colos and source locations throughout the world. And finally, we're excited to introduce this new topology tool. So this is unlike the map that I showed at the beginning of the presentation, which is part of our the dashboard on DoubleZero.xyz. This is a standalone topology planning tool where it takes effectively two inputs. It takes in the ISIS database, which is the routing database from a DoubleZero device, and it combines that with a snapshot of all of the serviceability and telemetry data that's written down to the DoubleZero ledger. And in this tool, we can now visualize and plan what certain routes might look like from a hop-by-hop basis. So we can put in a source colo, we can put in a destination colo, and we can compute the route the same way that the physical network would compute it, so that you can understand what the new latencies will be between two metro areas. This is an open source project. It runs as a Docker container. It's simple to install, and I hope you'll give it a try. We're actively seeking a network contributor to host this on behalf of the community so that we can put it out there. And we may host an instance of it ourselves as well, just as a matter of convenience. But it's a standalone tool. It can be installed on any computer running Docker. And we think it's a really good way to visualize the DoubleZero network and think about the performance implications of this network versus the public internet. And finally, I want to share some slides about Multicast. Now, Multicast is not a dark art. It is just a destination IP address. When you send a Multicast packet into a network, instead of replicating that packet many times to all of the interested receivers, which would be the model that's used in a unicast message passing system, Multicast shifts the burden of replication to the network itself. So in a multicast scenario, you have a sender, for example, a validator node, who wants to send a piece of information that it expects the whole cluster to be interested in receiving. And rather than using a message passing system like Turbine or a gossip protocol, Multicast can assist by sending that information one time into the network and allowing the network to build the tree structures and the topology needed to deliver that message to all of the interested receivers. We've worked with the teams at Jito and Anza to demonstrate what the performance implications of using Multicast are, both from a bandwidth perspective and from a message delivery perspective. Let's start with Jito. Jito offers a shred stream that many people use as the basis for receiving shreds sooner than they receive them from Turbine. And this is because Turbine is stake weighted. So if you are a lower staked validator, you might be interested to receive the shred stream because rather than waiting for your turn on the Turbine tree, you can get these shreds to replay and vote faster than you could otherwise. Now, in today's Jito architecture, the way that this works is shreds are sent to the Turbine route by a lead validator, but then they're also sent to a component of the Jito infrastructure, which fans out those shreds via a series of workers to the shred proxy clients. And this is just status quo. We worked with Jito to implement a version of their block engine, which in addition to unicasting the shreds it receives to the local workers in that region, it also connects to DoubleZero and sends those shreds over DoubleZero Multicast. So now we can create a shred proxy client that receives both the unicast version that's available today and a multicast version from DoubleZero. Let's see what this looks like at a global scale. There's 8 regions in which Jito operates where shreds are being produced. And generally, the consumers connect to the local worker in the region in which their computer is. So if the shred proxy on the right here is in Amsterdam, it has a unicast connection over TCP to a worker in Amsterdam. And in this case, we're going to set up to also have a DoubleZero connection in Amsterdam to receive the shreds over multicast, regardless of the region in which they were originated. With this topology in mind, we can set up a simple delta. Now, I'm a network guy, so the way that we like to make these types of experiments is to use packet captures. So we devised the test where a shred proxy joins the unicast feed, joins the multicast feed, and we collect a bunch of timestamps off the packet captures and just simply do a delta. So let's orient to the results. Higher is better on the left. On the left, you're seeing a view of the median through 99th percentile of the difference, where positive numbers reflect the magnitude of the win of the multicast feed. And on the right, you're looking at a more traditional histogram, where you want the area of the curves to be to the right of 0, because positive numbers indicate a win. Now, what we can see here is that when this Amsterdam computer that's joined to both the unicast shred stream and the multicast shred stream, when we make this measurement on the median, there's a 2 to 3 millisecond improvement. Now, that's not nothing, but importantly, there's over 10 millisecond improvement at the tails. And the tails is where most of the activity is. The tails exist because there's bursts of traffic, bursts of shreds, bursts of transactions, often in response to some economic activity or some movement in a price, or some trading that's happening. And this is where you care deeply about receiving information as quickly as possible. So 10 plus milliseconds at P99 is a remarkable outcome for simply adding a multicast into the stack and sending to a new destination IP. The story gets even better when you look in other regions. So if we set up a computer that's doing the same thing in Tokyo or in Frankfurt, we can see that the order of magnitude of the win goes up even further. In Frankfurt, there's quite a remarkable story here. You have the median is, again, 2 to 3 milliseconds faster, but in the tails, during this period where this was observed, even at P90, you're seeing 30 plus milliseconds of improvement. And on the right, on the histogram in Frankfurt, you can see that nearly all the cases of observations are right of 0. And so this is a far better scenario for someone who's trading off of these shreds, or someone who is in general wanting to vote or replay on these shreds. So why should you care about this? Well, all week at Breakpoint, we heard about internet capital markets and Solana being the cornerstone of that. Well, from my point of view, coming from the high frequency trading space, I know for certain that traders bring economic activity, right? And so we can't really have capital markets without all of these traders. The shreds are the information that traders really deeply care about, and the more transactions that we can bring from the trading community onto Solana sort of grows the pie for everyone. Now, the shred stream story is interesting, but we can also look at what multicast could potentially enable natively in the Solana software if we look at it alongside Turbine. So if you have a lead node in Frankfurt today, that leader, when it's receiving transactions and producing shreds, it sends the shreds to the Turbine route. And then it's the Turbine tree that sort of fans out all of those shreds to all the interested receivers, which are all the nodes in the cluster. We worked with Anza to modify Agave so that in addition to unicasting to the Turbine route, the leader would also multicast into DoubleZero. This way we could arrange another test where we have a validator, for example, in London, receiving shreds from the Turbine route, or from the Turbine tree rather, and also receiving them via multicast. And we can make a similar measurement. So we set up 2 receivers, 1 sender, and we log the shred receive time with the source. And we use those log messages and the timestamps alongside them to make a very similar measurement as we did in the Jito case. Now let's orient to this chart. These results are maybe not as intuitive to look at. The solid lines reflect the relative arrival time from the first shred of a given block. Now, there are a number of what are called FEC sets, and FEC sets are FEC is forward error correction, and this is the encoding that's used to ensure reliability in periods of packet loss. And really the metric that we care about is how quickly for each of these lines can we reach on the y-axis 32 packets. And with any 32 packets, we can recover the entirety of the transactions contained in those in each of the FEC sets. So the solid lines represent packets received from Turbine, and the dotted lines represent packets received from DoubleZero Multicast. And you'll note that the Multicast lines go straight up. So as they are received, there's no real tail, and that's because they're sent in batches into the network, and you're not waiting for Turbine to work out the ordering and to pass it along from one machine to another, which is where all these sort of tails are presumably introduced. Now the distance between reaching 32 from Multicast or via the Turbine tree is 100 milliseconds. Now, we said earlier that the Jito shred stream using Multicast could get you, 10 to 30 milliseconds at the tails. But this is during normal operations. Just by adding a Multicast destination to Agave, to the leader, we can receive the shreds 100 milliseconds faster. And so now this validator that's participating in Solana can receive all of its transactions, begin replay, begin voting, and it speeds up the entire chain. It's IBRL at its finest. So let's visualize what this looks like. We've put together this animation to try to show the difference between sending shreds over Turbine and sending shreds over Multicast. So when the leader who's in Frankfurt starts sending to Turbine, this is the sort of activity that causes these tails, these curves, right? You have all of these sort of circuitous routes and paths through various nodes in order to ultimately get the shred to London. And that causes that curve that you saw from the relative shred arrival time. And you'll see that when you have APAC involved, and you have to go all the way down to to Singapore or Tokyo, these are big hops, and they take many milliseconds, and that's how you can potentially recover 100 milliseconds in the next animation. So using the same leader in Frankfurt, let's visualize what it means to multicast. When you send the packet once into the network, now you're depending on the network to cascade all of that information out geographically. So of course, if you are in Frankfurt and our test was running in London, you're going to receive all of those shreds directly from Frankfurt via London over the fastest path between Frankfurt and London each time, with no intermediate computers. Now, if we take the same example and the same test, and we move the validator who's receiving shreds from London to Sao Paulo, there's an even more interesting dynamic, which is just the benefit of the DoubleZero network being faster. Now the shreds are, the first shred is actually being received 25 milliseconds before the turbine tree, or before it receives any shred from turbine. And the story holds in Frankfurt as well, when the leader and the validator under test are in Frankfurt. Now, the order of magnitude of win isn't maybe the same. It's maybe 20 milliseconds, but you're still talking about an incredible improvement with very little work. The time it took the ANSA engineers to adapt Agave to operate in this way was a matter of days, and that's because it's easy to code up to multicast. It's still just a socket. It's got some different socket options, but it's just another socket to write to. So why should you care about this one? Well, Turbine provides more than just shred dissemination. So this is not DoubleZero and Malbec Labs saying you should just blindly adapt this into the protocol, but it shows what could be if you did. It also shows that if Consensus started to using this, if Rotor and Alpenglow start to use this, you could see similar results. And most importantly, I want to demystify this idea that developing to multicast is hard. It's not hard. It's just another destination IP, and adapting the Agave code base to use it was a breeze. Okay, so what's next? Well, with 40% of Solana stake on DoubleZero, we are now shifting our attention to onboarding RPCs. We think the RPC providers experience landing transactions on Solana will be markedly better when 40% of the time you're connecting over in a dedicated network that's built for low latency, high throughput, and availability to the TPUs that are connected to it. So if you're an RPC provider and you're not on DoubleZero, let's talk. We've also been working on a proposal to Solana to turn on our edge filtering product. Edge filtering is an FPGA-based solution that we hope to bring to bear in 2026. And quite a lot of work has gone into ensuring that we can have these FPGA-based devices in line between transaction senders and the validators, and not to be disruptive to the quick sessions that are sort of the underlying transport protocol that's used to issue those transactions. So there's a proposal out with Anza, Firedancer, and the rest of the community to understand what we are proposing happens to the quick libraries that Solana depends on in order to introduce edge filtering. We also want to bring these first multicast use cases into mainnet beta. So we've showed some impressive results, and now we want to reap the benefits in a production context. So we're actively working with Jito to enable ShredStream and to over multicast and to bring the value to the clients. Likewise, we're looking to activate the network contributor community. The network contributors are such a core part of this whole DoubleZero story. And we need to collaborate with them on tooling and ops workflows and metrics and capacity planning to ensure that this is the best physical network that can be built for high performance distributed systems. So quite a lot of work will be going into 2026 to ensure that that community is alive and well and vibrant and developing really cool tools to keep this network performing at its highest level. And then importantly, we're trying to shrink the globe. Right? We can't beat physics. We can't beat the speed of light, but we can effectively shrink the globe by ensuring that we expand into new geographic regions, understand the fiber connectivity into those regions, and make sure that all of the connectivity that DoubleZero is using is the absolute fastest in the world. And that's how we can IBRL.